we'll go to the next speaker, which is Professor Tatiana Rappoport from the Universidade de Rio de Janeiro, which will talk about orbital Hall effect in 2D materials. So Professor Tatiana, thank you very much for accepting our invitation. And please, you can share your screen.
Okay. Can you see it?
Yeah.
Okay.
Sure.
So first, well, I think good morning there, right? It is a pleasure to present my talk in this workshop. I want to thank the organizers and Eduardo for the invitation. Well, most of the results I'm presenting today are done in collaboration with Roberto Bechara and Márcio Costa, which are my colleagues from Fluminense Federal University in Rio de Janeiro, Tarek Cisne, who is a postdoc there as well, and Luis Canônico, which is a former PhD student from UF as well, that's now in the group of Stefan Roche in Barcelona. Well, I will talk about orbitronics and more specifically about orbital Hall effect in 2D materials, but because this is something quite new, I will spend a long time giving an overview of the subject. So I will begin with that and motivate, this topic a little bit, and also relate this topic to a more general picture. So we know that our society has an increasing need to store and transfer data, and information technology induced industries in search for the energy efficiency and reducing dimensions. And 2D materials are ideal platforms for this new generation of devices. At the same time, we also know that spintronics plays a traditional role in information technology by using both the charge and spin-off carriers to encode this information. And to use spin to transmit information, of course, we need to inject spins in materials, that can conduct them well. And of course, we want the information to be there, so the information isn't lost. We need to manipulate the spins and detect them. And we want to do that electrically. But the main issue is that the electric field does not interact with the spins directly, right? So spintronics in general uses two key ingredients. One is magnetism, and in a very simplified picture of magnetic metals, there is an exchange interaction between the local magnetization and the conduction electron spins, and this will produce a shift of the band structure of spin up or spin down carriers, which of course will lead to a spin polarization at the Fermi level. And this is at the heart of several phenomena, from giant magnetoresistance to something more new like spin torque, where currents can exert a torque in a magnetization in a nanostructure. Another key ingredient is the spin-orbit coupling that, of course, influences the magnetism, but even in the absence of magnetism, it can play an important role on spintronics. And I think we all know that in the last 15 years or so, there were many discoveries and control of effects that rely on spin-orbit coupling, especially to generate spin currents and spin accumulations in non-magnetic materials. And this is root in the fact that in solids, the nice thing about the spin-orbit coupling is that it couples the momentum of the carriers with the spin. And in this sense, it will mediate the interaction between the spins and this electric field that cannot couple with the spins directly. And it will result in the possibility of manipulating spins without the need of the magnetization of a magnetic field. And since I think 2005, where the spin Hall effect was measured for the first time, different methods for spin injection and manipulation are using the spin orbit coupling. And some are beginning to be marketed, as for example, the new MRAMs, where the spin currents that are generated by a spin orbit coupling will exert a torque on magnetization that is used for information writing. So these are the several advances in spintronics lately related to the spin orbit coupling. Well, up to now, the role of the orbital angular momentum of the carriers for me was the mediation of this interaction between the spins and the electric field in materials with spin orbit coupling. But what I want to talk is an analog of spintronics where that operates with the orbital angular momentum of the electrons instead of the spin. And this is what it's coined orbitronics. So the first thing that comes to our mind if we begin to talk about orbitronics is, why do we need to use this orbital angular momentum if we already manipulate spin with success, right? And as I just told you, the spin magnetic moment will not couple with the electric field directly. However, if you think about the orbital angular momentum in a simple way in an atom, it is connected to a charge distribution, but at the same time, it has a magnetic moment. So in this way, we know that it can be manipulated with both electric and magnetic fields without the need, for example, of an exchange interaction or the spin orbit coupling. And this, of course, opens the possibility of using a large pool of material for this type of manipulation. Well, orbitronics is quite incipient. The name was coined by Berners-Vick, Hugh, and Zhang in 2005. So more or less at the same time of this famous work on topological insulators, they made a work on orbital Hall effect. However, not much was done in the field for almost 15 years, and many other interesting things came in the meantime, like topological insulators. And so this was kind of lost, but there has been a lot of activity, or I don't think a lot of activity, but more activity in the last 3 years or so. And we are beginning to see some experiments as well. So some of the spintronics effects already have orbital counterparts, at least theoretically. And the orbital Hall effect is an example, which is the counterpart of the spin Hall effect. Well, if you want to know a little bit more about orbitronics and what is done, there is this perspective article by Dong-Wook Goh and collaborators. Dong-Wook Goh is a very young researcher that has many nice contributions in orbitronics, so you can check this. It's a small review. Okay, but so we are going to talk about the orbital Hall effect. So let me just review the spin Hall effect. I think most of you are familiar by now, at least in general talks. So in the spin Hall effect, if we apply an electric field in a given direction, there will be a resulting spin current or in a transverse direction or a spin accumulation. And it can be observed in non-magnetic materials that have spin orbit coupling, a strong spin orbit coupling. And it has been used in semiconductors and metals to inject spins and spin currents in spintronic devices. There are basically two different mechanisms to generate the spin Hall effect. So it's divided in two subcategories. One is the extrinsic spin Hall effect. So the spin current is a consequence of the differences in the scattering of spin up and spin down states. And this difference can come from a spin orbit coupling, the impurity or the wave functions. And there is also the intrinsic spin Hall effect that depends on the interplay between the crystal structure and the spin orbit coupling, which will make spin up and spin down states respond differently to an electric field. And in this case, it doesn't rely on scattering, which is the case, for example, of topological insulators. Well, and what is the orbital Hall effect? Well, the orbital Hall effect is exactly the same thing, but instead of a spin current or a spin accumulation, we have the orbital angular momentum current. And most of the work on orbitronics so far is concentrated in the orbital Hall effect. And up to now, we only have calculations on the intrinsic orbital Hall effect. So the first proposal for the orbital Hall effect came in the same work where the name orbitronics was coined, in this work by Bernevig, Hughes, and Zhang, proposing orbital Hall effect in silicon. And we can see that, you know, in many years, there are only 3 works on Contani's group on orbital Hall effect in metals, and not more activity. And since 2018, there has been more activity in this field. Well, in analogy to spintronics, it's also necessary to transport an orbital current and detect it, right? And the main issue in experiments, it is quite difficult to distinguish the spin and orbital angular momentum accumulations, because, you know, the way you detect is you see a magnetic moment, and they both have magnetic moments, and they are detected more or less in the same way. So the strategy in 3D metals, where the first experiments are coming up, is the use of light metals with very weak spin-orbit coupling, so that if anything sizable is detected, it cannot be related to spin. It's a little bit more tricky than that, but I don't want to go into details. And basically, that's the main idea. So since last year, we are beginning to see novel results in different fronts. Well, in theory, one of the first questions that emerged is, when it comes to orbital, is the relaxation. So there is a lot of theory on spin relaxation in metals, 3D materials, semiconductors, but the relaxation mechanisms are different from the ones for spin. And there is always a question if it could decay too fast because of the interaction with K, and so any scattering is able to relax this orbital angular momentum. And well, the first theoretical work in relaxation processes is showing the contrary. So orbital angular momentum can be protected against relaxation, and the relaxation lengths can be longer than the spin ones. And a few months ago, we could see the first experimental results directly detecting the orbital accumulation of orbital Hall effect with MoG. So in these experiments, the authors, they use, again, as I was telling you, a light metal like titanium to generate the orbital accumulation through the orbital Hall effect. And they compare this with the spin accumulation of a much heavier material like platinum. And they see there is, you know, the sizable accumulation in titanium, and they argue, and they have other measurements to say that this is coming from the orbital Hall effect. Well, there are proposals of using orbital torques to switch magnetization in ferromagnetic layers, which means that inject an orbital current to switch the magnetization in ferromagnetic layers. And even before that, the experiments on spin orbit torque, several experiments on spin orbit torque, were pointing out that the orbital torque was an important contribution to the total torque. But this year, there was a first controlled experiment using, again, a light metal to finally characterize the orbital torque and compare it with a typical spin torque. So we are beginning to see experiments on orbitronics. Well, other orbitronic effects, effects that are counterpart of spintronic effects exist as well. One of the first to be discussed and measured was the orbital Rashba, that can be measured by circular diprism. And similar to the spin counterpart, it can be important in the generation of orbital currents. There is also the orbital Edelstein effect, where an orbital angular momentum accumulation can appear in a plane under the effect of a longitudinal electric field, like we see with spins. And both the orbital Hall effect and the orbital Eisenstein effect are results of the existence of these orbital textures. But there is an important difference between what we see in spintronics and these orbital textures, because these effects can occur now in central symmetric crystals, which is not the case of spin textures that depend on breaking, on having a non-central symmetric material. Well, let me begin to discuss a little bit a mechanism that links the orbital textures with the orbital Hall effect. And one mechanism that does this link quite well is equivalent to the one presented in the famous work of Jairo Sinova and collaborators from the PRL from 2004. So if there is a, let me review it a little bit. If there is a spin texture, it means that K and the spin are locked because of the spin orbit coupling, which we can see here. And in the presence of an electric field, there will be a dynamic in K space. So the Fermi surface, which is just this circle into the materials, will be displaced by an amount which is proportional to the electric field at a small time, right? Well, this will change the texture in the new field. So this can be seen as well as a new time-dependent magnetic field that appears. So while moving in momentum space, the electrons will experience an effective torque which tilt the spin-ups for py positive and down for py negative, creating a spin current in the y direction. Well, this theory is based on the dynamics of magnetic moments. It's a semi-classical approach, and it's valid as well for the magnetic moment of orbital angular momentum, as we show in one of our works. Well, it seems quite nice, but this is not the whole story, because different from spins, it is possible to have an orbital texture without any orbital angular momentum, as it was discussed in this original paper of Don Wook. So let's imagine a very simple model with only px and py orbitals in that same circle that we were seeing before in the Fermi energy. So it's possible to have an orbital texture in that Fermi surface, which is given by this equation, which is a real superposition of px and py, which means that in all points LZ is 0. What they show in this work is that by applying an electric field, the dynamics, which in this case involves the hybridization with another band, can change these superpositions and produce a complex linear combination between px and py that now can carry orbital angular momentum. So it's not, so without any electric field, there was no angular momentum in the system at all. And it only appears when we turn on the electric field. But this, of course, is not the only possible mechanism. So as I was showing another mechanism in the previous slide. So I believe that in orbitronics right now, we are in the part of the development of a field where we need to understand the different possible mechanisms that can lead to this effect. And in some way, it's more rich than in the case of spins, because it's possible to generate the orbital angular momentum just by applying an electric field and changing this linear combination. And I think all the possible mechanisms leading to these effects is still an open question. Well, now let me move to my interest in particular, which is 2D materials and the orbital Hall effect in 2D materials. And I believe this is specifically interesting because of the combination of having multi-orbital systems and low dimensionality, which we know that can be quite interesting for orbital physics, because crystal field can split these energetically the states and separate the different orbitals in energy. So this is why we focus on 2D materials. Well, orbital Hall effect began to be explored in 2D materials in 2020, so it's quite new. And I think I didn't update this list, but until the end of the year, these were probably most of the works in this subject. And I will narrow my results to 2 of our works. And I'm doing this to narrow it a bit and look at the orbital Hall effect in transition metal dichalcogenides. And I will start with the monolayers. Well, I believe that by now you are heard of them. So they are a layer that are composed by transition metals in one sublattice of a honeycomb lattice and a pair of chalcogens in the other sublattice. So this system isn't centrosymmetric. Well, the TMDs, they have a few characteristics. They are in the H phase, they are semiconductors. They also have the K and K prime values as graphene in the Brillouin zone. And because they don't have inversion symmetry, they can have value physics. Each value can be addressed by circularly polarized light. They also present value Hall effect. I will discuss this a little bit later. But as this image shows, it has a spin valley locking, which means that for each valley, the state that's close to the gap has a defined spin. And together with the idea of addressing a given valley with light, this can be used for spintronics. So it can be used for spintronics, but at the same time, we know that TMDs, they have a neglecting spin Hall effect in the vicinity of the band gap. So they don't have spin Hall effect close to the band gap. So these are the main characteristics. Well, I will begin showing some results on orbital Hall effect in TMDs. And for those that want to calculate this using Kubo formula, this is more or less the same way as we calculate the spin Hall effect, but we use the orbital angular momentum operator of the orbitals in the type binding Hamiltonian instead of the spin to define orbital current. So it's very similar to the way you calculate the spin current with the Kubo formula, but we change the operator. Instead of using a spin operator, we use an orbital angular momentum operator, and I will go back to that at the very end of my talk. And we can also write this Kubo formula in terms of orbitally projected Berry curvature as well. So it's a way we write it here. Well, back to business, we begin with the simplified 3D orbitals model for the TMDs. And this model is well known and works well near K and K prime. The LZ operator in this basis can be written like this. And here is the band structure of MoS2 with spin orbit coupling and without spin orbit coupling. And here in red, we have the spin Hall effect. So you can see that without spin orbit coupling, we don't have spin Hall effect that we should expect. Here we see that there is no spin Hall effect in the gap. And in blue, we have the orbital Hall effect. And surprisingly, we see a nice plateau of the orbital Hall effect inside the TMD gap. And not only that, but when we see this plateau, we see that it has more or less the same intensity, regardless of having or not spin orbit coupling, so definitely not related to spin orbit coupling. We can look at the orbital textures. Let's focus on the color. So LZ is positive for red, and is negative for blue. Here we have the 1, 2, 3 are the 3 bands of the 3 orbitals model. On top, it's the system without spin-orbit coupling, and on bottom we have the with spin-orbit coupling for the 2 spin configurations. But when we see the, let's focus on the valence band. When you see the valence band, the orbital textures of the 3 different valence bands, they are the same, right? And we can see that there is a locking between the LZ and the valley. So the orbital valley locking precedes the spin valley locking in TMDs. So actually the spin valley locking is a consequence of the orbital valley locking in these systems, which is important. So it doesn't really depend on the spin orbit coupling, as we should expect. But at the same time, we know that this system has a broken inversion symmetry. And because of this orbital valley locking, there is a question that maybe we are seeing that orbital Hall effect plateau because this is just a signature of the valley Hall effect. So we want to dig on it. At the same time, we see this plateau and we ask ourselves, is this topological or what, right? So let me talk a little bit about topology, very superficial. So my talk doesn't have that many equations. It's more like an overview of the field. But there are a few things that I want you to pay attention when I talk about, I want to show a Berry curvature in different situations. So I will begin reviewing a few aspects that I feel I will need later. So we know that the quantum Hall effect is the quantized version of the Hall effect and one of the first clear manifestations of topology in band theory. And we can think of our Hamiltonian as an operator that gets every point in the Brillouin zone and give us a spectrum and age states that has a smooth variation in K. So if we walk around a closed loop in this space, which is a torus in 2D, the wave function accumulates a phase, that is the Berry phase, but it ends up that because of this geometry, the accumulated phase can be either 0 of a multiple of 2 pi. And a good way of calculating the Berry phase is through the Berry curvature, which is defined here. And we can rewrite the integral of the Berry curvature in a way that it gives us an integer number, which is the Chern number. And each isolated band below the Fermi energy has a Chern number. And the sum of these Chern numbers gives the plateau in the Hall conductivity. Well, I will discuss, as I told you, the Berry curvature in different situations in the next slides. But I want you also to think that although we calculated the Chern number for the Hamiltonian for H, other operators can also do something very similar to H. They can map K in the parameter space. They can have a gapped spectrum, and we can also calculate their Chern number. So using their agent state. So the Chern number can be associated to other operator that's not just the Hamiltonian, right? So, so because I want you to see a few Berry curvatures, let's begin with graphene at low energy. We can write just this Dirac equation. We have the 2 inequivalent points K and K prime. And we can break time reversal symmetry in this system with including this mass term, which is proportional to tau z, which is the isospin of the valleys, and sigma z of the sublattice. And this is basically the model proposed by Haldane in 1988. So this is a quantum Hall effect without an external magnetic field. And if we look at the Berry curvature of the system and the spectrum, if you look at the spectrum, we see that this is the spectrum of graphene with a mass term, so it has a gap. And if we calculate the Berry curvature, it has the same structure for K and K prime. We can calculate that integral for K and K prime, and the sum of the integral for K and K prime will give us the Chern number of the system. Well, we can also have a very similar system, which is graphene, but instead of breaking time reversal symmetry, we include a spin orbit coupling, which is basically two copies of the Haldane model, which is the model of KNML, presented in 2005 for topological insulators. And now the mass term is proportional to tau z and sigma z, but also has the spin. So we have a copy for spin up and another for spin down, with the mass is inverted, right? And if you look at the spectrum is more or less the same. It's the same actually. It has this same gap if lambda is equal to delta. And but when we calculate the total Berry curvature is 0, but if we calculate the Berry curvature per spin, we're gonna see that it has the red Berry curvature for one spin, the blue Berry curvature for the other spin. And we can calculate, we can think that SZ is a good quantum number here because it commutes with the Hamiltonian. So it can, so the spectrum of H can also, and the eigenstates of H can also be used to calculate the Chern number of the spin. And if we do so, we can just sum the Chern number of K and K prime for spin up and subtract from the Chern number of K and K prime for spin down. And we obtain what we call the spin Chern number that can also characterize the topological phase in this system. Well, also we could include just a mass term, which is proportional to sigma z. And in that case, we break, different from the other two cases, we break inversion symmetry. We also have the same gap, but now we have a positive Berry curvature for K and negative Berry curvature for K prime. If we integrate this in K space, the total Chern number will be 0, but we can subtract the Chern number from K and K prime and define a valid Chern number, which will be finite, and this characterizes the Valley Hall effect. So with these ideas in mind, so different Berry curvatures and what we can calculate with these Chern numbers, let's go back to our system and see if that was just the Valley Hall effect. So to see if that was just the Valley Hall effect, an easy way to solve this issue is to calculate the orbital Hall effect in a bilayer MoS2, because bilayer MoS2 is centrosymmetric. So if we do so, this is the spectrum of the monolayer, this is the spectrum of the bilayer. In this case, we are not using the 3 bands model, but we are using DFT calculation. And we can see that we still have the plateau for the monolayer. When we calculate the orbital Hall effect for the bilayer, we not only have a plateau, but we have a plateau that's twice the size of the plateau of the monolayer. So it's not related to breaking, to having, you know, a non-centrosymmetric system. This orbital Hall effect persists in this specific case. And the plateau is twice the size, so it seems like something that's topological, right? What we can do for the bilayer TMD is to look at the low energy Hamiltonian. This is quite well known. Then I think about this, and what we do with this low energy Hamiltonian, we only use the two bands that are close to the gap. There is a third one we are not considering in this system. And if we look at the basis that we use, it's nice that because this is an eigenstate of L equals 0, and this is an eigenstate of LZ plus and minus 2. So if we do so we have this band structure. We can calculate the Berry curvature projected in the layers. And we see that, as we should expect, the total Berry curvature is 0, although for one layer we have positive Berry curvature in K, and for the other layer it's negative, and the other way around for K prime, but the total Berry curvature is 0. If we calculate the LZ projected Berry curvature, as I was presenting in a previous slide, what we see is the two Berry curvatures are finite. So there is and if we can sum this and calculate the total orbital projected Berry curvature, this is a finite number. And this is why we can see a nice plateau when we integrate this and calculate the orbital Hall effect. Well, of course, the orbital angular momentum is not a good quantum number in these systems, but we can still calculate the orbital Chern number using an approach developed by Émile Brodin that he used for the spin and even for other operators. So what we do is we use the orbital angular momentum operator, which is projected onto the valence band states. And we diagonalize this operator. And if the spectrum is gapped, we can use the eigenstates to calculate the Chern number. If the spectrum is not gapped, we cannot do anything with it. But and if it's gapped, we can use the eigenstates to also calculate some sort of Berry curvature, and then again calculate the Chern numbers. Well, in our case, the spectrum is gapped, so we can calculate, and this curvature is well behaved. We can calculate this Chern number, and we obtain it is 2 for the bilayer and 1 for the monolayer. But this is per valley, right? In a valley, right? Well, we can now go back to the DFT calculations and look at the ribbon. If we cut the system in a ribbon and look at the LZ projection of these states, for the monolayer, we can see that there is this LZ K locking, because in K and K prime we have a different polarization of LZ, which is clear here. For the bilayer, it's difficult to see, but we have almost degenerate edge states here, and we have the two different projections. The thing is that when we apply the electric field, LZ positive goes in one direction and LZ negative goes to the other direction. So we can have this spin accumulation, or orbital accumulation with the electric field. Well, so this is what we obtained in these works, right? Now I want to discuss something a little bit different, and it's the question of, I was discussing, okay, it's clear for me now that it cannot be 100% related to the Valley Hall effect, because the moment we put a bilayer, we still have this effect. But still, there is a problem, in my opinion, with the whole definition of the Valley Hall effect, because there is no clear observable for the Valley Hall effect, right? So, and I was quite bothered by a small detail when I was working with the orbital Hall effect, that we are using the atomic orbital contribution to the orbital angular momentum, but we know that the modern theory of magnetism shows that there is a contribution from the band, which is quite important in 2D materials exactly because of the valleys. And we know that, for example, in twisted bilayers, there is a huge valley magnetic moment, right? So this valley magnetic moment is an important contribution. So recently, Scientica, Bowo, and Giovanni Vignali defined an orbital angular momentum from the magnetic moment, according to the modern theory of magnetism, and used it to calculate the valley Hall effect as an orbital Hall effect. So they use so we can use the same methodology that I was discussing before, but instead of using for the current operator using my atomic orbital angular momentum, we can use an angular momentum that's defined through the magnetic moment of the modern theory of magnetism. And using the same methodology, I believe we are capturing the two contributions, for example, in the case of the TMD. So, well, these are the results from Giovanni Vignali and Scientica Bowo, which I think are important because they quantify this orbital Hall effect, and they show that it depends on the size of the gap. So it can be stronger if the gap is smaller, right? Because it's related to the Berry curvature and the magnetic moment that's coming from the modern theory of magnetism. Well, if we do the same in our case, we don't need to compare the valley Hall effect with the orbital Hall effect anymore. We can use this approach to calculate the orbital Hall effect. And by doing that, we are considering these two contributions in equal footing, right? So we just sent a paper to arXiv using this approach. And we can see that qualitatively, the result is more or less the same. So we still see a plateau, but in terms of the quantity, there is a reduction in the plateau of the orbital Hall effect when we consider the two contributions. The other interesting thing is that we are used to calculate, for example, the magnetic moment of a valley as it's just a scalar, but we show in this work, and we discussed this in this work, that when we have the generic state or almost the generic states, actually, it's necessary to take into account an non-abelian structure for this orbital magnetic moment. So we have a matrix structure, which is way more rich. And we use this matrix as an operator to calculate the orbital current in these systems. So I think now we are in a place where we are calculating and taking into account these two effects. Well, finally, although we calculated the Chern number of LZ that helps us to understand that plateau, we still didn't know what topological phase could be associated to the orbital Hall effect in the plateau, and I think we still don't know precisely, but this is getting more clear now. So for a long time, the topology community missed that the 1H TMDs are in fact high-order topological insulators that are characterized by corner states in the armchair X. And this is something that appeared in at least two papers last year. And for a long time, we knew that the orbital Hall effect was a result of the interplay between the orbitals and the lattice symmetry. But now we have evidence that the orbital Hall plateaus in insulators, they are actually witnessing the high order topological states in 2D materials, because we are doing our work considering a very large amount of data, where we see that the orbital Hall effect can witness a high order topological state in a 2D material. So the moment you have these corner states, you have a high order topological insulator, you also have an orbital Hall effect plateau. So this is a work that's in preparation. Well, finally, if we further reduce the symmetry of our system, and that can be done cutting the system, as in the case of one of our works, but it can be done actually by considering a system with lower symmetries. It's also possible to see magnetoelectric effects like the orbital Wildenstein effect. So in a recent work, we explored this a little bit more. So we showed that in a nanoribbon of px and py orbitals in a honeycomb lattice, we can see this magnetoelectric effect together with the orbital accumulation of the orbital Hall effect. So, and this is something that we can see in TMDs as well. So if we get if in a ribbon we get the orbital accumulation in the length of the ribbon, what we see that we can separate our contribution in a symmetric and antisymmetric contribution. The antisymmetric contribution can be associated to the orbital Hall effect, but there is also a symmetric contribution that's associated with an orbital Wildenstein effect. That depends on the existence of edge states in the system. So, well, with this, I think I go to my final remarks. What I try to show here is that multi-orbital 2D materials can host large orbital Hall effect in the absence of spin-orbit coupling. This can occur in metals and also in insulators that are called orbital Hall insulators. We saw that TMDs present sizable orbital Hall plateaus. In this case, it's not that strange. We do have edge states. They have a topological origin, but there is still a lot to think about, especially regarding to the orbital Hall effect mechanism and what exactly is driving this orbital Hall effect, especially in these insulators. But something that I want to bring here is that the orbital Hall effect will widen the pool of materials that can be used for spin orbitronics and spintronic devices, because now we can couple system with orbital Hall effect or other orbital effects to systems that have strong spin orbit coupling and then also are magnetic as well. So we are widening the possibilities for the interplay between all these effects. Well, thank you very much for. Oops.
So thank you very much, Tatiana, for this nice talk. So we have time for some questions.
I don't know why I don't.
So questions. So Eduardo, go ahead, please.
Thank you, Tatiana. Very interesting talk, and I think I have several questions, but I'm going to start with one that is really difficult to me to see what is the meaning. When you show the 1T phase of the MoS2 has fraction of charge in the corners, how do you calculate that?
No, this is okay. This is the H phase actually. It's the normal phase, the most common phase. Okay.
Yeah, 1H. Okay.
Okay. Yeah. So the things that you have to cut it in a way that you have. So if you cut and you have zigzag edges, you don't see anything, right? You have to cut because, of course, the zigzag edges will make them metallic, right?
Yeah.
So if you cut it in an armature edge, and then you go to inside the gap, you're gonna see that you're gonna have inside the original gap, right? You're gonna see some almost degenerate states, as you can see here, and if you look at these states. the charge distribution will have this corner states like you see. So here, here is the spectrum of this, finite system. And you have to do that. Okay, you have to do that with ab initio calculations. And for tight binding calculations, the problem is that this 3 orbitals model is not able to capture this effect. And this is why for more than, because I had this feeling of the crystalline topological insulator for a long time, for more than 2 years. And I tried many times to cut my system. I couldn't see anything. But it's exactly because you cannot have this armchair states, and if you have only these 3 orbitals model, you are not able to see them. But if you use a more sophisticated model, you can see by cutting it in armchair, you can see the states, the corner states. They are very clear.
Yeah. Okay.
You can also, there are other ways to calculate the high order topological phase. There are some recipes, and it works as well.
Okay, so and how do you associate the 1/3 of the electric charge to that corner states, or because in your figure there's 1/3 of E, right?
No, this I'm not exploring. This is just a glimpse of a new work. I'm not exploring.
Okay.
This is just to show you that there is a relation between these 2 things, and this is what we are exploring now. But I didn't explore this in my talk, right?
Yeah.
These 2 things, and it's not that clear for me. I can. There are things that I can connect, and I think there still cannot connect in terms of. But I see a few things that happen in this type of systems that can explain the orbital Hall effect, but not exactly the corner stick, but some band inversions that we see in this system.
Yeah.
Band inversions.
Yes, because I have the same problem. I work in a little bit in higher order topological insulators, and then there's some connection that I could do. Okay, so thank you. Well, I don't know if someone else.
Any other question? So I have a little question. So you mentioned you work with the orbital angular momentum, and next you include the orbital magnetization according to the modern theory, which is a quite different concept. So in that case, in the case of orbital magnetization in 3-dimensional metals, biosemimetals, for example, it is proportional to the Berry curvature, and hence the Chern number is proportional to the topological charge of the band crossings. So what happened in this sense with the angular momentum contribution? It is topologically protected or something else?
Well, this is a good question. Well, what we know is that, well, let me go back to what we did first, right? Well, we can think that we were including the angular momentum. That's, that's the one that's inside the atomic angular momentum, right? But we were not, if we think about a package, we were not including the self-rotating, the angular momentum of the self-rotating package. So we have to, so in principle, we do have to include it, right? Because if you want to calculate the orbital Hall effect of the whole thing, we need to think about the angular momentum of the atomic one and the self-rotating as well. Yeah. So, but it's true. So the magnetic moment will be proportional to the Berry curvature. Mm-hmm. And now this is then something that I want to discuss, right? Basically, so basically my main point here is the following. We spent a good time, we as a community, right, condensed matter physics, discussing the modern theory of magnetism, the Berry curvature, and then the magnetic moment. Okay, now what happens with this magnetic moment and all that if I apply an electric field, right?
Mhm.
So the idea is what happens with this if I apply an electric field. So I'm going to have magnetoelectric effects that are related to the existence of this Berry curvature of the magnetic moment. And this is what I see in these calculations.
Yeah.
Yeah, but there is still to think about it, right? This is what is not very, I'm not very convinced with just the idea of having the valley Hall effect. I'm more convinced with the orbital Hall effect because there is a magnetic moment that's originated in the valleys. But there are things with symmetry that we still need to understand because, for example, the sign of this orbital Hall effect, it's always the same when I use this approach. And I think it has to do with the fact that the magnetic moment it's related to the Berry curvature. But this again has to do with the self-rotating package and how it is with an electric field that will rotate it in the same direction depending on the orientation of the electric field. So yeah, there are things to answer in this approach.
Yeah. Okay. So thank you very much. So any other question? So Daniel, go ahead, please.
Thank you. Thank you for the nice talk. I just had a question about your last slide. So you're asking whether you've seen symmetry protected topological phases. And so in general, for these sort of electron interactions are supposed to be relevant, right? They talk a lot about short range entanglement. But here, sorry, maybe I missed it, but I didn't see where the entanglement entered into the picture.
Where, so in what slide? This one?
Yeah, in this one, well, it's just a matter of definitions perhaps, but as far as I knew, symmetry protected topological phases, the definition usually given is that interactions are relevant and you have entanglement between the different parts due to the interactions, right? But in your talk, maybe I missed it somewhere, but I didn't see any role being played by interactions or entanglement being part of your picture.
I'm not including interactions here, right?
Yeah. Okay. So are you okay? So maybe it's a matter of definitions because symmetry protected topological phases are usually entanglement is supposed to be very important for the definition. So I don't know if you meant more like I don't know, like crystalline topological phases or something like that.
Yeah. So for crystalline topological phases, you can use, for example, something like a Chern number to define this as well, right? In terms of the eigenstates of a symmetry, right? You can define a symmetry that there is a line, for example, where the system is invariant under the symmetry, and then you can define a Chern number as well, right? And you don't need, for example, to talk about correlations or entanglement to define this phase. So it's not.
Okay.
Right.
Yeah.
So any other question? Okay, well, if we don't have more questions, we thank again to Tatiana for this nice talk. Thank you very much, Tatiana.
Thank you.
So now we have the break. We see you here at 1 p.m., 1 more hour, please. Yeah.